Hi guys, welcome to the next lecture. We've already seen two ideas behind the concept of derivatives. As I mentioned in my very first lecture of derivatives, that we will be viewing it from 3 points of view. Okay, so हम तीन तरीकों से इसे देखेंगे, and today it's the third part that we will be dealing with. We will look at the derivative in terms of rates of change. And then finally, we will connect the dots. We will connect everything. So we will be learning today how slopes and rates of change are related to each other. It's the same concept dealt a little differently. Let's recall velocity. We have seen what velocity is. It's associated to speed, right? But it's speed in one particular direction. So as such, velocity, what is it telling you? It is basically the rate of change in the position vis-a-vis the time. So velocity can be viewed as a rate of change of position with respect to time. But rate of change is not restricted to only velocity. Rate of change could be associated to various things in life. For example, a microbiologist might be interested in the rate at which bacteria, the number of bacteria in a colony changes with time, right? An economist might be interested the rate at which production cost changes with the quantity of a product that is manufactured, maybe, right? A medical researcher might be interested in some rate of change related to, say, the radius of artery. If somebody is, some medical researcher is working on coronary heart diseases or something, so they might be related to alcohol consumption and the changes in the radius of artery, right? So the rate of change is such a concept which could be applied in various things, various subjects. There is no stoppage to it. So why only view it as velocity? But yet, of course, velocity is one example of it. So let's keep our next objective to understand if I have any function y. If I have any function y, what is the rate of change associated to it in case I change the input? Let's understand the rate of change of y with respect to x, where y is a function of x. I'll take two cases. First is a simple trivial case of a linear function. So suppose you have y in terms of x, because it's a linear function of x, it will say look like mx, the usual notation that we give, mx plus b. Okay. So we would be interested in figuring out how y changes in case I change x. In a linear function, what happens? This m that you see here, which is said, which is called slope. So slope is a natural measure. We can say it's a natural measure of the rate of change in y with respect to x. So it's naturally happening. Why it's happening? There's a reason behind it. Why is this a fixed rate of change here? There's a reason behind it. Let's see what it is. Let's understand the why and how behind the concept of that the rate of change in case of linear function y equals to mx plus b will always be m. So what essentially happens here is that if you change, this is your x-axis and this is your y-axis. So your x-axis values are here, x values, and y values are depicted here. So what is happening here is that when x is 0, the value that you get is b. So this much is b. Now, if you change 1 unit in x, if you change 1 unit in x, so suppose this is 1 unit. What's the change in y that occurs? This is the change that occurs in y. If you will take the same length here, that is again 1 unit, you will observe that exactly same length occurs here. And this length is nothing but m. there's a jump of amount m. If there's a jump in x of amount 1, there's a jump of amount m in y. That's what is happening every time. Formally speaking, a 1 unit increase in x is always producing m unit change or increase in y in this case. If you may take an example and work with values. So I'm going to take the general case only. So your y is mx plus b. Now, if I change x to x plus 1, what is the change that occurs in y? We want to ask what change occurs in y. Let's try to figure out. So y will become, the new y will become mx plus 1b. So I'm going to quote it as, say, this is y0, then this is y1. Or, so what is the change that is occurring in y with respect to change in x? So the new y is this. The change in y that is happening is the new y minus the old y that we had, which is mx plus b, right? So mx plus m plus b minus mx minus b. And that clearly gives you just m. So what do we get to know here? We get to know that there is a change of m amount in x. And when you look at the rate of change, it's a rate, it's a ratio of the change in that occurs in y upon the change that occurs in x. The change in y vis-a-vis, when we say rate of change, that means change in y vis-a-vis or with respect to the change in x. Again, that turns out to be m. In the next process, if you would want to take the case where x plus 1, now you add another 1 to it and it turns into x plus 2, you would notice again the same thing is happening. And that's why when you have a linear function, you will always have a fixed rate of change. And that's the slope that you can relate to, okay, very easily, to y equals to mx plus b. The slope is the measure of the rate of change in y with respect to x. This was case 1, which was the case where I took a linear function. A linear function gave you this line. A linear function. Now, what if the function is not linear? You have a curve, something like this maybe. Well, in that case, again, we have a fixed rate of change. Well, no. Since you can see the curve keeps on changing, sometimes it's going up, sometimes it's going down. So, of course, there's no fixed change happening. So, there is that is where the rate of change concept becomes a very, very essential and important. Because we can clearly see with this graph itself that the rate at which the function is changing will differ from point to point. It will not remain the same. It is not a constant like in the case of a linear function. Before I formally tell you everything, let's just on the graph look at it. So when I change 1 unit of x here, what's happening? That's the kind of change in y I get. So I would like to take another unit of x. So I'm going to increase x by another unit. This time I'm getting only this much amount change in y. So can you yourself see that this length and this length, they're quite different. In fact, it's almost like half of it. And if I go up more, take 1 unit change in X and now look at the change in Y. Well, it's very, very small change. If I start from this side, now 1 unit here, I'm reducing X. I'm going back here by 1 unit, and I can see that Y jumps out here. And then reduce X by 1 more unit. Y is here. Okay, so what you can see here is that the whole idea is the rate of change is constantly changing. The rate of change is not a fixed value, right? So when you have a general curve, the scenario will not be same as a linear one. It can be, the rate of change will keep on changing. Okay, let's look at the concept more formally now. I'm sure you can see in this diagram the idea that I'm trying to pour in here, that the change in Y that occurs from a 1 unit change in X tends to have a greater magnitude in regions where the curve rises or falls rapidly, in comparison to the regions where it's happening slowly. Okay, so there will be a change in rate of change. So here also, just like what I did in velocity, I differentiated between 2 points. So 2 points as in the average rate of change and the instantaneous rate of change. So let's talk about average rate of change here. Average rate of change of Y with respect to X over a certain interval. So if you will take an interval and try to see the rate of change of Y with respect to X, it will be, so if I may call it average rate of change, it will be the change that occurs. Say I'm taking x0 to x1. So the new functional value will be fx1 and the old functional value is fx2. So I'm going to take the average. So I'm going to take the difference in this upon the difference that occurs in x. So that will give you the rate of change in y vis-a-vis or with respect to the change in x. Now, the changes are not as smooth as you can take in an average. Okay. So therefore, there was an idea that I tried to develop even in the velocity part. What if I want to know what is the rate of change at a particular instant? What if I want to know the rate of change at a particular instant? We did realize there that at an instant, how can you define change? That was another part of the mystery. But we did realize that we can look at the change by taking the chord. So if suppose this is the graph of the function and I'm interested in figuring out what is the rate of change at this particular point, I would be interested. Let me just give you the idea again geometrically what it is like. Suppose your point x0 is here, x1 is here, and the functional value that x0 gives you is fx0. The functional value that x1 gives you is fx1, which is here and here, as you can see. Then clearly this horizontal length that you see here, this is x1 minus x0. And this vertical length that you see here is fx1 minus fx0. So clearly the slope of PQ is perpendicular upon the base, which is fx1 minus fx0 upon x1 minus x0. The whole idea of instantaneous rate of change. Now, this is the average rate of change, as you can see. This is nothing but the average rate of change also, right? And it's also the slope of this chord or the secant line. This is the slope of the secant. If I keep on taking it back here and create a unique point where this secant touches this curve, which will be just P. That is when Q is actually turning into just P. Or in other words, what are we doing? We are diminishing this difference So the difference between x1 and x0 is just diminishing to 0. If that happens, then it will be a unique point where they're touching, where this secant is touching, and it becomes the tangent. We have done that concept of tangent, and that also gives you the instantaneous rate of change. So in the instantaneous rate of change, what basically is happening, your x1 minus x0 is almost turning to 0, which is the change in x. Change in x is almost turning to. In other words, we can say that the rate of change, instantaneous rate of change, is when x1 is actually tending towards x naught only, fx1 minus fx naught upon x1 minus x naught. This limiting value will give you the instantaneous rate of change. It's rate of change, but at one particular instant, that is just at P. So here again, I will repeat myself as I worked with you in tangents also and velocity also, that it doesn't mean that the change is exactly 0. No, then of course this number will not be defined. We're not saying that, but it's very close to. It's almost at P. It might not be exactly, but it's almost at P when x1 and x0 are so close to each other. And that's how you define instantaneous rate of change. Notation wise, you can refine it a little bit. You can say x1 minus x0 is equal to, say, h. That is the change in the input x is h. Then your rate or average rate would turn into f of x1 is equal to x0 plus h. So f of x0 plus h minus f of x0 upon h, and your instantaneous rate of change, the instantaneous rate of change will turn into limit h goes to 0, f of x naught plus h minus fx naught upon h, right? The whole idea behind this case that I've done with you guys is that the rate of change is a concept which is not just particular to velocity. It has various or varied applications. It can be used in so many ways, and this gives birth to the concept of derivatives and differentiation. So in a nutshell, the idea of derivative, we've seen it in 3 ways. One way was velocity, tangents, and the third way, rate of change, right? All lead to the same idea, the idea of derivative. The idea of derivative is essentially telling you what is instantaneous rate of change, but there's a whole process to understand what would be the meaning of instantaneous when it comes to change. Okay, so that's why we've done what we have done in these 3 videos. Now this will give us an idea to something called the derivative function. So this gives us a way to proceed to something which is called derivative functions. As you must have understood with the what we did in rate of change, the rate of change is a constant when it's a linear function, but it might not remain constant. जरूरी नहीं है कि वो हमेशा ही constant रहे. It can take different values. So in itself, it becomes like a function. In itself, it becomes like a function. Before I end this video, I also want to give you the actual idea of the concept of derivative. The concept of derivative deals with what happens if I change something. What is the impact of that change, right? So suppose I start with function x square. Suppose I want to visualize x square. How would you visualize x square? It's very easy visualization. If you take a square with side x units, square with side x units. So if you take any square with side x unit, what is the area of this square? It's x square. Well, the function that I was interested in, x square, could be seen as the area of a square whose side is x. Great. Now the whole idea is what happens when I make some changes in x. That's the whole idea when we were working on rate of change. That was the whole idea. What happens when I change a little bit in x? Then what is the impact? So I'm going to see the impact that it gives to my function x square, which actually is the area of the square. So हम क्या करेंगे? We will just increase this side by h unit. So we have increased the side by h unit, and that will provide me a new square, which you can see in dotted red line. That's a new square that I have. And the sides of this square is x plus h. Now area would now turn into x plus h square. So you can open the whole square. I've already done that for you. X square plus h square plus 2xh. Now, if I'm interested in rate of change, what am I actually interested in? I'm interested in what is the change that occurs in the new area vis-a-vis the change that I have made in x. So rate of change would be, if you want to know just the change in y, then you will just subtract the value, new area minus old area. But if you want to know the rate of change, then it's going to be the change that has happened to the area, and the change that occurred to the area is x plus h whole square minus x square. That's the change that occurred in the area when I changed x by h. The new side was x plus h. So the change that has occurred in x is h. So let's look at this rate of change. It's going to be x plus h square plus 2hx minus x square, whole thing upon h. And what's going to happen here? You will have x square cancels. You can take h common. You have h plus 2x, whole thing upon h. H cancels, and what I have is h plus 2x. That's the rate of change, which we say is the average rate of change. It's not the instantaneous rate of change yet. For instantaneous rate of change, what will I do? For instantaneous rate of change, I will give the limit, take the limit as h goes to 0 of h plus 2x, and that will give me 2x, my friends. So that means what I get as the derivative of x square is actually 2x. The change that has happened in the area of this square when I changed the side of the square by h units, the change that is happening is 2x. Now, what you must note here for the next video, what you must understand here is that 2x is dependent on x. 2x is dependent on x, so it's a function of x in that sense. The moment you will give different values of x, you will generate different values of the rate of change in x. And that gives birth to the concept of the derivative function, which is something that we will be learning next. Thank you.